Okay, today we're going to go over the power series, or power series in general. More specifically, the way to find the interval of convergence, IOC, and the radius of convergence of a power series. So what is a power series? A power series is a way to define a function as an infinite series. Now, I'm going to write out the general term for a power series, or an infinite power series, I suppose. So of course you have your typical n equals 0 to infinity expression of a sub n. However, every power series features the term x to the power of n. More specifically, x minus c to the power of n. And this is where a function would be centered, or where the power series would be centered at point c. Now, of course, if c is equal to 0, then you'll have x to the power of c rather than x minus c to the power. Sorry, x to the power of n rather than x minus c to the power of n. So there are a few things I want to go over. Power series have what's known as an interval of convergence and a radius of convergence. Those being the interval of convergence being the points at which the series will converge depending on the value of x. And the radius of convergence is simply just like, I suppose, the length of the interval of convergence, if that makes sense. So define those intervals of convergence or radius of convergence is quite simple. You're going to want to use the ratio test. Now, if you recall, I've made a video on the ratio test. It states that if you have the limit as n approaches infinity of a sub n plus 1 over a sub n, if it happens to be less than 1, then the limit will converge. Or sorry, so the series will converge. Now, this applies to power series. However, x is undefined, no matter what the outcome of the limit is. So, for instance, if I were to give you the limit, the ratio test of a power series, we'd end up with the limit as n approaches infinity, a sub n plus 1 times x to the power of n plus 1. That is if the function is centered at 0, over a sub n times x to the power of n. Now, if this happens to be equal to 0, and there are rare instances in which it is equal to 0, if it happens to be equal to 0, then the radius of convergence and interval of convergence of the series is infinity. That's because 0 happens to be less than 1. And if this happens to be equal to 0, no matter the value of x, then it will converge no matter what. However, if this were to be equal to 0, well, we know from the interval convergence or ratio test, we know from the ratio test that infinity, well, you should know this anyways, that infinity is greater than 1, meaning that this will converge at, will diverge at all times except for one point, and that one point is at c. That's because, more specifically, when x is equal to c. That's because if we were to put down the general term x minus c to the power of n, but put c in place of n, we'd end up with 0. So this right here is equal to 0. And so you're multiplying one of the terms by 0, meaning that you're going to have at one point at which the power series is going to converge if the limit is equal to 0, or if the limit is equal to infinity, and that point is x equals c. Now, typically you can abbreviate radius of convergence by just saying ROC. Typically we would put with the notation of the radius of convergence and interval of convergence, the radius is just some value. In this instance, it's going to be equal to 0. That's because you only have one point at which it converges, and the radius of one point is 0. Now, the interval of convergence is typically represented by like a range of functions. Let's say that the power series converges from 1 to 3, from x equals 1 to x equals 3. Well, then your interval convergence would look something like that, like this. However, in the instance at which the interval of convergence is only 1 point, you just put the 1 point, which in this case will be c. Now, there's one final sort of outcome of the limit test or sorry, ratio test. And this is the one that we're going to go most depth into. So I erased a bit of stuff. But as I said, we're going to go over an example where the limit is equal to some sort of constant. And this is the most fun. So by the limit or ratios test, if you have the limit from n equals 0 to infinity, the absolute value of a sub n plus 1 over a sub n, if that happens to be less than 1, then you'll have your series will converge. So what happens if we set what we have to less than 1? Meaning, what happens if our limit is less than 1? Well, we would have to essentially manipulate the equation such that we can find the value of n, or sorry, the value of x. And from there, we can find the interval of convergence. So let's say that our limit here, the one given, is equal to like 1 over a constant, let's say e. Now, that's a terrible example. 1 over a constant m of x minus c. Now, we have to set that less than 1 in order to find the interval of convergence, and therefore the radius of convergence. So what we're going to do here is we're going to multiply both sides by m, at which point we'd end up with the absolute value of x minus c is less than m. Now, the absolute value of a function suggests that we have to assume that x minus c is greater than m, and x minus c is less than negative m. So let me draw that up here. So if the absolute value of x minus c is the absolute value of x minus c is less than m, then not only is x minus c less than m, but x minus c is greater than m, negative m. Now from here we can find the true interval of convergence. In both instances, you'll add c to both sides in order to find the value of m, and so you'd end up with negative m plus c is less than x. That comes from this equation over here, this inequality, and x is less than m minus c. Okay, I apologize for what just happened. I accidentally stopped screen sharing, but I rewrote everything that I previously had. So if you look down here, you'll see that negative m plus c is less than x, and m plus c is greater than x. Now from here, you have the radius of convergence, and you technically have the interval of convergence. However, you don't know the endpoints. So for instance, let's say that you have a power series centered at 0, and you end up with an interval of convergence of negative 3 is greater than x is greater than 3. Well, since x is centered, or the power series is centered at 3, you have a radius of convergence of 3. Now, the interval of convergence, on the other hand, can be represented by negative 3, 3, or negative 3, 3 with an open bound, or any combination of the two. And so you need to test the endpoints. You need to find whether the power series you have converges at x equals 3 or x equals negative 3. If they don't, then of course you'll have to use open bounds. If they do, you can use a regular bounded interval. It's practice problem 1, and in fact, the only practice problem we're going over today, because it is late at night at the time of which I'm recording this. So first thing to take note of this expression, the infinite series of n equals 1 to infinity of x to the power of n over n times 2 to the power of n, is that x is centered at 0. That's because the exponential over here can be rewritten as x minus 0 to the power of n, meaning that it is centered at 0. So keep in mind that c is 0. That's going to make it easier to find the radius of convergence. So now what we have to do is employ the ratio test. So first we'll write the limit as n approaches infinity, the absolute value of x to the power of n plus 1 over n plus 1 times 2n plus 1 over x to the power of n over n times 2 to the power of n. And we have to say that that is less than 1. However, from here we can simplify our limit further. You can say that this is equal to the limit as n approaches infinity of x to the power of n times x. This is equivalent to x to the power of n plus 1 over n plus 1, of course, times 2 to the power of n times 2. Again, that's equal to these two terms over here are equal to is equal to 2 to the power of n plus 1 multiplied by the reciprocal, not quite the reciprocal, multiplied by n times 2 to the power of n over x to the power of n. If you're confused as to why I managed to do this, it's because I'm merely just manipulating the quotient over here. Okay, and again, this is less than 1, but we can simplify this further. So 2n is found in both the numerator and denominator, so we can cross both of these out. X to the power of n is as well. So again, we end up with, or I suppose we could simplify this further. We can say that this is equal to the limit as n approaches infinity of the absolute value of x times n over 2 times n plus 1. And this is less than 1. However, we can still simplify this further by pulling out the x and the 2. So is equal to the limit as n approaches infinity. Sorry, let me rewrite this actually. This is equal to x over 2 of the limit as n equals infinity of the absolute value of n over n plus 1. Now, if you're curious as to why I was able to pull out x over 2, it's because that fraction isn't altered by any way. It's not dependent on the value of n, and so it doesn't need to be part of the limit. And finally, this is less than 1. So from here, we can just manipulate it further. The limit as n approaches infinity of n over n plus 1 is equal to 1. So we end up with x over 2 is less than 1. Okay, so forgive me because I made a mistake. I realized that halfway through the last video. So this over here is, we improperly simplified it. So this over here, let's just completely disregard this last row. This expression over here, what previously was written as x times n over 2 times n plus 1, we're going to rewrite that actually as 2n plus 2. We're simply distributing the 2. So from here, what we're going to do to make this fraction a bit nicer is divide both the numerator and the denominator by n. We're just dividing the whole fraction by n. So let me rewrite that over here. This is equal to the limit as n approaches infinity of x over 2 plus 2 over n. And just, again, I'm just dividing by n. Now, finally, we can say that this is less than 1. Now, if we were to use this limit, if we were to replace n with infinity, well, this fraction over here, sorry, this denominator would be equal to 2 plus 2 over infinity. Now, any number, any fraction with a denominator of infinity is equal to 0 because it's infinitely small to a point where it might as well be modeled as 0, meaning that this over here, this limit is equal to the absolute value of x over 2, and that is less than 1. So that means not only is x over 2 greater than 1, sorry, less than 1, but x over 2 is greater than negative 1. So from here, we can multiply both sides of both equations by 2. And so this top function, this top inequality is equal to x less than 2, whereas this bottom inequality is equal to x is greater than negative 2. So since our power series is centered at 0, we can tell that our radius of convergence is equal to 2. I'll show you why. Let's just call this point C. Let's call it this point 2. Let's call this point negative 2. So our power series converges, let's just call this 0, in this interval here. Now, since it's centered at 0, the radius is going to be equal to half of the total length of the interval of convergence, meaning that the radius of convergence, I'll put it up here, is 2. Now we're not yet done. We have to test the endpoints. the power series may or may not converge when x is equal to -2 or x is equal to 2. So that's what we have to do at this point. Okay, so I just cleared everything. Let's again say that the radius of convergence is 2. It's centered at 2. Our interval of convergence, we may as well say for the meantime that it's from -2 to 2. However, this could be a bounded interval. We have to test the endpoint. So let's say let x equals negative or positive 2 for the time being. So that means that the interval, or sorry, the infinite series from n equals 0 to infinity of x to the power of n over n times 2 to the power of n can be rewritten as 2 to the power of n over n times 2 to the power of n. Now, you can see that we can simplify this by quite a bit. We just have to cross out the both instances of 2 to the power of n, and this is now equal to the infinite series from n equals 0 to infinity of 1 over n. Now, you may not be familiar with harmonic series, but this absolutely diverges. We can say that this series over here, actually we can't put the therefore yet because we haven't completed this. We can say that this infinite series diverges by harmonic. Now, a harmonic, the proof that something diverges by harmonic is just a specialized case of God, what is that called? The P series infinite series test. I made a video on the topic in the past. If you're curious as to what the P series test is, just go watch it. So we've already found that when x is equal to 2, our series diverges. So this over here should stay unbounded. Now we have to test when x is equal to -2. So we're going to write our infinite series with -2 in place of n. So the infinite series from n equals 0 to infinity of -2 to the power of n over n times -2 is indeed equal to the infinite series from n equals 0 to infinity of -1 to the power of n times 2 to the power of n over n times 2 to the power of n. Now, it's important to point out that -2 to the power of n is actually equal to -1 times 2 to the power of n. And what we're doing is we're just distributing the exponent. So that's why I was able to expand it. Now from here, we can just cross out both instances of -2 again. And so I'm going to rewrite this a bit. Our infinite series is now n equals 0 to infinity of -1 to the power of n over n. Now, although this over here, our other infinite series when x is equal to 2, although that happens to diverge, this in fact does not diverge. It converges by the alternating series test. Now, normally you have to put all your proof that this converges by the alternating series test. Actually, in fact, I don't think you do. Normally you would, but this is what's known as an alternating harmonic. So again, it's just a specialized instance of the alternating series test. So we can say that our infinite series converges by alt harmonic. So we know that when x is equal to -2, our power series converges. So this over here is going to be bounded. While this over here on our rightmost value of our interval of convergence diverges. So when x is equal to 2, our power series diverges. So that's it for today's video. If you have any suggestions, please put them in the comments below. Thank you.